we'll be moving heavily into homework number 3 material today. So I'll make that available shortly. So we'll be starting to build some circuits. We got to Ohm's law at the very end of last time, so let me just quickly recap on that, and then we'll move forward. So first of all, we're going to have these regions of conductors in our circuits. Those are these voltage plateaus, and then we're going to let charges flow between these plateaus, these equipotential regions, by going through these things called resistors. If you have a higher voltage on one side of a resistor and a lower voltage on the other, then these hypothetical positive charges will flow from the higher voltage to the lower voltage. Again, it's really electrons going the other way, but we have this convention and we use it. The direction of what we call electrical current, I, is in the direction toward lower voltage. I, again, just a reminder, it's literally the charge that flows per time. The units of it are coulombs that flow per second, which is called amps. So the whole reason why they would bother to flow through such an obstruction, a resistor, is because you are offering a reward. The reward is getting to lower energy. So a positive charge going from higher voltage to lower voltage loses energy. That energy, by the way, we say it loses potential energy, but it goes not to kinetic energy like on homework 2. We're going to harness it for going to heat, and so that's one of the first things that we're going to do today after this little review is we're going to calculate how much goes into this thermal energy. Again, there's an energetic reward, and and because it's incredibly common, we do switch to a notation. When we say V in Ohm's law, what we really mean is the voltage difference between the two ends of the resistor. So the V is really the magnitude of delta V. Again, I know this is terribly confusing, but it's so common that you have to kind of get okay with that. So starting with homework number 3, when we say V, we really mean the voltage difference between one place and another place. So all three of these things interrelate. V is the voltage difference across the resistor. That's your motivation. Why would charges burrow through an obstruction? It's because they have an energy reward for doing that task. So V sets the motivation for the charge to do this. Over on the right side, we have the product of the current and the resistance. The current is literally what happens, how much flow there is, and then R is the difficulty. R is a rating for how difficult it is to burrow through this particular obstruction. So basically the equation is motivation equals what happens times difficulty. You should be able to flip it this way and that. I have mentioned a couple cases already last time. For instance, for a fixed amount of motivation, if you fix the motivation, but you increase the resistance, then the current will get less. With a high resistance, you can get the current to slow down to basically a trickle. And likewise, if we fix the difficulty, we fix the difficulty of how difficult the obstruction is to move through. If you increase the motivation, then more current will flow through that very same obstruction. So that's basically Ohm's law. You should really understand it fundamentally, understand all these relationships. They use this equation regularly for blood flow. So you're going to, when you study the vasculature, you're going to see this equation again. The stand-in for voltage, which is your reward, in blood flow, it's the change in pressure across the blood vessel. So why would blood flow from one place to the other? It's because there's pressure difference between the two ends. Instead of current, you usually use Q, and by Q, this is physics 1 Q. This is either volume per time or kilogram per time. So that's not Q like charge, that's Q as we used it in physics 1. And then in blood flow, resistance is resistance. So there's various reasons why blood vessel would have more or less resistance. Some of them are actually in common with electrical resistors. So again, huge application to medicine. Okay, so this is electrical stuff, and this is blood flow or any kind of fluid flow. Very useful. So we have to get a couple things out of the way before we start building our circuits. So one of them, I guess I should tell you a little bit about, is resistance. So resistance is a rating for how difficult or how easy it is to get through this particular obstruction. So let's talk about the units. The units of resistance are going to be the units of voltage over the units of current. So the units of voltage are volts, that's hence the nickname, and the units of current are amps. And we give a name for this, we call it an ohm. So this is called an ohm. That's actually a capital letter omega. Okay? So we call it an ohm after the person who came up with Ohm's law. Okay? And his name sounds like a Greek letter, so they gave it the Greek letter ohm, omega. So basically what 1 ohm is, 1 ohm is an obstruction that if you gave it a 1 volt difference, so you gave a motivation to go across it of 1 volt, it would allow 1 amp to flow. Okay? That's one way to visualize how much resistance does 1 ohm present. If you give a motivation to go across it, 1 volt, then it does not allow whatever you want to flow through there. It allows 1 amp to flow. Okay? Now that's just a rating for how resistive it is, but what are the things that go into how resistive it is? The R actually depends on the physical construction. Physical construction of the resistor. Most oftentimes, if I'm asking you about this, I will give you the obstruction as being a cylindrical or kind of a rectangular block. So charges have to flow through it. Let's say the higher voltage on this side, charges have to flow through it like this. So the physical properties, one of them is the cross-sectional area, so basically how wide is the tube. The second is the length of the tube. And then, as you can probably guess, it also depends on what it's made out of. So that will tell you it's an empirical rating for how tough is it to bob and weave through the atoms in this particular material. So the final equation is this. Let's take a look at each term here. This is basically the equation which will tell us how much resistance a particular thing will put up based on its physical properties. So first of all, you notice that the resistance is directly proportional to the length, which means that if you increase the length, what happens to the resistance? It increases. Makes sense. You have a longer tube to get through, more stuff you have to burrow through. The gauntlet is longer. And the equation from experimental evidence, we find that it is directly proportional to the length, which means that if you double the length of the tube, you'll double the resistance. Okay? So that's one factor. The resistance is also inversely proportional to the cross-sectional area, which means that if you increase the cross-sectional area, what's going to happen to the resistance?
Goes down.
It's going to decrease. Hopefully this also makes sense, right? Whenever you see construction and they're widening a highway, it's because they want to make it easier for people to commute through there, right? So if you widen the tube, it's going to make it easier. Remember, this is not just one charge. This is a whole bunch of charges that are coming through at once. And if they can go through side by side instead of having to go in single file, then it's a lot easier. So widening the tube, that will also decrease the resistance. Both of these factors also apply for blood vessels. You make it longer, it has more resistance. You make it wider, it has less resistance. And again, experimental evidence indicates that these are inversely proportional, so if you double the cross-sectional area, what's going to happen to the resistance? half, right? You can have a circular cross-sectional area and use pi r squared, or it can be a rectangular block. You don't have blood vessels that are rectangular blocks, but maybe you have, say, a block of material you're using as a resistance. And then the final factor is what accounts for the properties of the material. Now, you could, of course, go nitty-gritty and think about, well, it should matter on the exact crystal structure and a density of the thing and everything like this. But we just don't worry about any of that stuff. We just get an experimental value. So we send charges through something and we see how much resistance it puts up. This is called the resistivity of the material. We use the Greek letter rho for that. That's basically commonly what it's notated with. It's unfortunate because we also use that for density. It's not density, it's resistivity. Okay? The units of this, if you work it out from the equation, are actually ohm times meters. I don't have anything particularly significant with that interpretation. It's just that that's what it comes out to be from the equation. So this value basically tells you what is the range. Now this could be anything from 0, which means that there's absolutely no impediment to flow whatsoever, all the way up to infinity, which means it doesn't allow anything to flow through. That would be the extremes of this. 0 would be an ideal conductor. This would be something, remember we said that you have this vast store of free electrons in the conductor that they can just wander around wherever they please. They're totally free, so there's nothing stopping them from going wherever they want to go. And we also said that we called something an ideal insulator. And an ideal insulator, all the electrons were bound to particular nuclei. They couldn't just drift off and go somewhere else, even if we applied a voltage that they would want to trace. They would want to move accordingly. Well, this is where I finally introduced to you the idea that there's really, these are two extremes. We've put two things into bins where it's not really two bins that are separate. It's a continuum. So there are things like, for instance, typical metals that are very close on the grand scheme of things toward the 0 end. And so for us, we take these as approximately 0. So for us, the parts of the circuit, like the battery terminals and the wires and things like that, those are equipotential planes, right? So for us, the conductors are equipotentials. Things like battery terminals, wires, things like that. And so you can freely traverse that without any cost. So since they have no resistance, they have no voltage drop across them. So since the resistance is approximately 0, the voltage drop across them is approximately 0. And again, remember there, by V I mean voltage drop. So that sets up the plateaus. Otherwise, we take things over here, things that we consider as having non-zero resistance, we call these our resistors. So basically, we are still going to have our cake and eat it too. We're basically still going to kind of put a breakpoint in here somewhere. Now, where is that breakpoint? Well, again, it's completely arbitrary. But to simplify our situation, we're going to take certain parts of our circuits and say there's no resistance, and other parts where all the resistance is. Okay? So for us, the conductors are equipotentials, and then the resistors themselves, the resistance is not 0, and we use Ohm's law to figure out how things flow through them. So our approximation is basically this. We have equipotential plateaus. These are our conductors, conductor, conductor. And then to go from one to the other, these are our resistors. We have a series of plateaus, and we move between these plateaus through resistors. I should mention that realistically, really it looks like this. It's like that. So really, even a wire has some resistance, and so if it has a little resistance, it'll have a little voltage drop across it. Okay? So this has small resistance, and therefore a small voltage drop across it, and same thing here. But of course, the big show in town is the big resistor in the middle of the circuit, which presents a lot of resistance to flow, and therefore, that's really the action. So the resistor here has a very large resistance in response, and therefore has a large voltage drop. Okay? So just for simplicity, we assume that we're moving between equipotential plateaus through these special things called resistors. In reality, it's not that simple. Everything has resistors. Resistance is just that some things have less, far less, and some have far more. Just to give you an idea, if you compare a typical resistor that maybe is made out of, I don't know, typical way to make a resistor is a hunk of carbon. If you take a chunk of carbon that has exactly the same size and shape as a typical hunk of, say, copper, the carbon is about 2,000 times the resistance. So we call that the carbon resistor. That's basically the big show, the resistance in the circuit. We neglect the resistance of the wires themselves. One of the problems in your homework number 3, I'll ask you to account for the wires, but for the most part, if you see a wire, you can just neglect the resistance in that wire, okay? So that's what we're up to. You can see that we've loosened the restriction a little bit between ideal conductors and ideal insulators, but we're still kind of acknowledging the fact that there can be a wide gap in resistivity, and therefore resistance in the circuit. Now, there's no such thing as an ideal insulator. Everything will, if you try hard enough, you can get electricity to flow through it. There actually is something called an ideal conductor. It's called a superconductor. It presents exactly 0 impediment to electrical flow. They have not figured out how to make one of these that operates at room temperature, but they do exist. Okay, so if you can figure out how to have a material that has absolutely no resistance to electrical flow at room temperature, you have a Nobel Prize awaiting you. Okay, right now I think they're up to about 77 Kelvin. Okay, so that's one thing. That's what resistance is. It's how much current will flow given how much motivation you put across it, and you can determine the resistance based on the physical properties of what it's constructed with. I think there's a resistivity table on your equation sheet. I can't remember, but if not, it will be given to you in the homework or exam problem. The final order of business before we start building circuits, we know that we lose our potential energy to heat, so let's calculate an equation which tells us about that. I guess I should copy over here along with Ohm's law. So these are kind of our equations. V equals IR, that's one. The resistance, if needed, you can calculate it based on the physical properties. I should mention that most problems you don't need to do that. It's just handed to you. 100 ohms, whatever, just gives it to you. If you buy commercially manufactured resistors, it's actually just written there on the side. They often use a color band system but they're basically just telling what it is. So this is rare that you have to compute it on your own. And then the final thing we have to do is calculate this. So we know that we lose potential energy by having a charge flow across the voltage difference. So that's the amount of potential energy that's lost. Now that alone is not very useful. because, of course, once you turn the circuit on, it continuously dumps more and more potential energy. So as more and more charges flow across the resistor, more and more heat is generated. It just keeps going up and up and up and up. So a better way to describe it would be the rate at which it's done. We have a name for energy per time. It's called power. So this is the power dissipated by the resistor. It's the amount of energy converted per time, energy that's converted from electric potential energy into thermal energy per time. It's the rate of energy conversion. It's a much more interesting quantity. If you were to talk about the total energy outputted, say, by a light bulb, which is basically just a resistor, then the total energy that it's outputted depends on how long ago did you turn it on, right? It continuously outputs more and more energy as you leave it on. So it's much more interesting to talk about the rate, okay? So it's basically making it fair, right? It's the amount of energy conversion per time. So first of all, let me remind you what the units are of this. Power is energy per time. We call that a watt. So 1 watt is 1 joule per second. So for example, a 100-watt incandescent light bulb, what does that mean? Well, 100-watt is a light bulb, when you plug it in the recommended usage, dissipates 100 joules per second. It converts 100 joules from electric potential energy into thermal energy per time. Okay? So that's the unit. We'll get more into light bulbs in just a second, but let me also figure out a better way to describe this. Let me group charge per time. What's charge per time? That's current. And we have long since stopped calling this delta V. We've been calling that V. So if you want to get the rate of energy dissipation of a resistor, the power dissipated, you multiply the current that flows through it with the voltage drop across it. This has a very nice interpretation, by the way, because current is just charge per time, right? It's how much is coursing through there, how much charge is coursing through there per time. And voltage, let me remind you what voltage is, right? It's energy per charge. So since you're flowing to lower voltage, positive charge is flowing to lower voltage, you're losing that. So the voltage will tell you how much energy loss occurs per unit charge. So look at that. The charge is just the middleman, right? What you end up with there is energy loss per time. So you're losing energy, you're dissipating potential energy to heat by having a bunch of charges going through there, and each of them are losing so and so much energy. Okay? Does that make sense? So that's one of the equations that we're going to need in our circuit analysis, P equals IV. And I will also point out that we could come up with two alternative equations by subbing in Ohm's law for this. For instance, I could plug in V equals IR. So I put it in there, so I get I times R. So that's I squared times R. Or I could sub in Ohm's law to get rid of the current instead of the voltage, and I would get V squared over R. So those are three different alternative forms of the power loss equation, the power dissipation equation. You may wonder why we want all three of these ready-made. They're going to be very handy when we get to more complicated circuits and we have three different choices to grab from. So let me add those to the list over here. So we have three different options for the power law. Right off the bat, let me use the third form, the last one, to make a point about light bulbs. So P equals V squared over R. Now, when you go and you buy a light bulb, it says so and so many watts on the box. But guess what? it is actually not doing anything when it's in the box. It is not dissipating any energy to heat, right? So rating it by wattage is making a bold assumption, okay? It's assuming you're going to use that light bulb as the manufacturer intended. So you put it in a light switch where it has access to normal voltage, and also it's not on a dimmer, because you can have it all plugged in and then take the dimmer to 0 and it dissipates 0 watts, right? So really a light bulb, which is just a resistor, the inherent property of the light bulb is what is its resistance. It's not wattage, but it will always have the same physical construction, so it will always be the same amount of resistance, okay? So the inherent property is resistance, not power. So it's actually assuming, let's say you have a 100-watt bulb